Hello everyone, welcome back to online survey video tutorial on applied hydraulics. In the previous class, we have seen the Kaplan turbine and the Francis turbine. So in this class, we are covering up the draft tube and its types and the draft tube theory. So let us see what is draft tube, by the way. See, it is a pipe of gradually increasing area. So where one end of the tube is connected to outlet of the turbine or outlet of the runner. So and the other end is connected to a tail race channel. So which is used to discharge water from the outlet of the runner to the tail race channel. And so as I told, it is used to discharge water from the outlet of the turbine to the tail race channel, and one end is connected to the outlet and other end is connected to the tail race channel. And so what is the important point is the lower end of the draft tube should be submerged below the water level inside the tail race channel. So under all operating condition, you should make sure that the lower end of the draft tube is kept inside the water level in the tail race channel. So that is the main point. And what are the purpose of providing this draft tube? So basically, so what is the draft tube will do? So it will create a negative head, okay, or a suction head, so on the runner exit. So if the negative, because of this negative or suction negative head, so what happens? So it will, the net head on the turbine will get increased. So if the net head increases, then the efficiency will increase. And also, so this will make the possibility of installation of turbine above the tail race level without head loss. So because of the creation of or the development of this negative head, so we should make sure that we are going to install the turbine above the tail race channel so that there will be no head losses. And also you can inspect the turbine properly if you provide the draft tube. So and also, so it will convert a large portion of kinetic energy which is rejected at the outlet into the useful pressure energy. So or else what happens? So all the kinetic energy will get wasted. So that is the one advantage what we are getting by providing a draft tube. And also, so as the net head increases, so it will increase the power and also efficiency of the turbine will increase. And the pressure will be equal to atmospheric pressure if we not provide a draft tube. So in that particular case, we cannot discharge water freely to the tail race channel. Okay, so at that particular case, there will be head losses. So that's why, so to minimize the head loss, we have to provide a draft tube. So head loss will be minimum. So for a turbine with a draft tube. And coming to the types of turbine, you have the conical or a straight divergent tube and simple elbow tube, Moody spreading, and elbow with the circular inlet and rectangular outlet. So these are the different types of draft tube which are used. You can see the figures how this draft tube will look like. And so in case of this different types of turbine, the conical and Moody spread draft tube so are more efficient. The types of draft tube, and simple elbow and elbow draft tube with a circular inlet and rectangular outlet so will require a less space for their installation. So and also, so for a conical turbine, the angle should not be more than 8 degrees. So if the angle is more than 8 degrees, then it will increase the losses. Okay, so there may be a there may be a erosion of the pressure will be high, and due to that, so eddies is going to form, and also because of that efficiency will reduce. Okay, so if the angle is greater than 80 degrees, it will reduce the efficiency of the turbine. And the next you have a draft tube theory. So to explain this draft tube theory, so let us consider a draft tube. You can see here, so where one end of the draft tube is connected to a outlet of the runner or a turbine. So where that will act as the inlet. So and so one other end of the draft tube is kept inside the tail race channel. So and here we have considered two section, that is section 1 and section 2. Section 1 at the inlet of the draft tube and section 2 at the outlet of the draft tube. So you can see here in the figure, so inlet and outlet of the draft tube, and here y is the depth of the submergence of this draft tube inside the tail race channel, and hs represents the head from the inlet to the tail race channel, height from the inlet to the tail race channel. So as we have considered section 1 and section 2 at inlet and outlet of the draft tube, so let us apply the Bernoulli's equation. So you already know the Bernoulli's equation, that is sum of the energies at any section is same. That is, so sum of pressure energy, velocity, kinetic energy plus the datum energy, so remains constant. So that is the Bernoulli's equation. So if you apply the Bernoulli's equation here at section 1 and section 2, so you will get P1 by rho g plus V1 squared by 2g plus H plus Y is equal to P2 by rho g plus V2 squared by 2g, plus there is no datum head at section 1, and plus head loss. So there is a head loss from section 1 to section 2, that is denoted as HF. So and here in case of this particular section 2, you can see P2 by rho g is exposed to atmosphere. At section 2, the pressure will be atmospheric pressure. So P2 by rho g will be equal to PA by rho g plus Y. Okay, so if you substitute that in the above equation, so you will get, so P1 by rho g is equal to PA by rho g plus V2 squared by 2g plus HF minus V1 squared by 2g minus HF. So this equation represents the equation of draft tube. And the next you have the efficiency of a draft tube. So efficiency is defined as the ratio of actual conversion of kinetic head into pressure head, so in the draft tube, to the kinetic head at the inlet of the turbine. So we know efficiency is output by input. Okay, input is a kinetic head and output is conversion of kinetic head into pressure head. So here, so you know, the efficiency of a draft tube is denoted as eta d, so which is equal to actual conversion of kinetic head into pressure head divided by kinetic head. So where for that we have considered V1, V2 as the velocity or the inlet and outlet of the draft tube, HF is the head loss. So this actual conversion we know, so actual conversion is theoretical conversion into coefficient. So the theoretical conversion is given by V1 squared by 2g minus V2 squared by 2g. So if we considered head loss for this, that will be your actual conversion. So it will be V1 squared by 2g minus V2 squared by 2g minus HF. So that is the actual conversion of kinetic head into pressure head. So this is the efficiency of a draft tube. Thank you all. Let us continue the next topic in the next class.